So we've got a parabola, y equals x squared, our basic parabola, and now we're going to look at what happened, what do we remember happening when you change the number in front of x squared. So the first one here in blue, if you had 0.5 x squared, do we remember how we went about graphing that? Do we remember what that did? So you might have remembered in like your regular parabola, you went over 1, up 1, over 1, up 3. Now in this blue one, you would go over 1, up a half. And then over 1, up 3 halves. And it made your graph wider than you had to begin with. When that a value was 2, you might have remembered that instead of going over 1, up 1, you went over 1, up 2, then over 1, up 6. And that had the effect of making your graph narrower. With the negative out in front, we've already seen that negative on the outside of the graph. So here in black, negative 0.5 x squared. Well, that would make it wider and make it go down. And finally, in purple, again, made it narrower, but the negative out in front made it go down. When we start to look at patterns in all functions, we start to notice a pattern with the y values. Again, with this a value out in front, I'm going to say that the 0.5, the 2 are outside of the function. Can you see that in the green equation, that 2 is not getting squared? It's just 2 and then the x is getting squared. If I needed the 2 to get squared, I need brackets around the 2 and the x. And so I'm going to say that this is outside of the function. And as a result, we're going to notice that affects our y values. For example, on my original graph, I'll label this point. Would you agree on your parabola, you have the point 2, 4. And now, you have the point 2, 8. The x value hasn't changed, but the y value has changed from 4 to 8. We could pick another point. We could pick 1, 1, and now on the green graph, I have 1, 2. My x value hasn't changed, but my y value has become 2. What rule could I do that would change 1 to 2 and 4 to 8? Same rule. I mean, you could make a rule different, add 1, add 4, but that's a different rule. Is there a rule that I could do that's the same for both of them? How do I change a 1 to 2 and change a 4 to an 8 with the same rule? Do you want another point, or do you got it? Right, the next one on here in the red would be 3, 9. And in the green, we would have 3, 18. What's happening to the y coordinates? They're just doubling. What number do we have on the green equation? At 2. That 2, what it does is double your y coordinate. So the thing that we're looking at today is how do numbers stretch or compress a graph, and how do they affect the coordinates? All right, there's a bunch of graphs here. Take my camera out. So if you turn the page to 194, what we're going to look at is our square root graph. And on our square root graph in green, we're going to label this point 16, 4. And the question is if we graphed all of these other square root graphs with a number in front, first of all, I want you to notice that that number is outside of the function. It's not inside of the square root. So far, everything we've done that's been outside of our function has affected things vertically. It's moved things up and down. It's flipped things vertically over the x-axis. And now we have numbers out in front. We're going to notice that that changes things vertically again. So instead of 16, 4, with a 2 out in front, on our green graph, I'd like you to label this point is 16, 8. Notice the y-coordinate has been multiplied by 2. What do you think happens to the y-coordinate if you have a 3 out in front? Well, if we look at the point on the blue graph, we now have 16, 12. Compared to the red graph, which is our parent graph, which is our base graph, can you see the y-coordinate has been multiplied by 3? Does it work with fractions? If there's a half out in front, ooh, that looks orange. Yes, there's a good color. Sure enough, the y value has been multiplied by half. And in purple, so if we make a little note, I mean, they called it a root x. That value of a affects the y-coordinate. So when we multiply a function by a number, it will either stretch it or compress it. And we would call these vertical stretches and compressions. And the way a vertical stretch works is, imagine you grab a hold of your graph and you pull it away from the x-axis. So this red graph, if it got pulled away from the x-axis, it would stay stuck at the x-axis, but I've stretched it up to hit the green one, stretched it up to hit the blue one. If the number in front is less than 1, it's like I took this red graph and pushed it down to get to the orange one, pushed it down to get to the purple one. So we call any time that it is extended away a stretch, any time that it's compressed towards the x-axis, a compression. Next, we're going to look at what happens. Oh, sorry. Got to go back here, take another picture of what happens when there's a value inside of the square root or inside of the function. Again, we've got the red graph is our regular square root, and the point that they chose to look at was 4, 2. Now something interesting happens with the number inside. Unlike the number outside, which multiplied by exactly what you would think would happen, when I have a 2 inside my graph, the point on that graph is 2, 2. So we notice it's the x value that's changed. which makes sense since everything so far that happens inside a function has affected things horizontally. But instead of multiplying our x value by 2, you could say that your x value has been multiplied by a half, or you've divided by 2. And the language that I'm going to be using more is multiplying, but multiplying by the reciprocal. So if the number was 2, which is 2 over 1, you're now multiplying by 1 over 2. If the number is 4, you would multiply by 1 over 4. So on our blue graph, we have the point 1 comma not 4. One comma 2. But when the number inside is a fraction, for example, in this orange one, I take that fraction and do the reciprocal, I'm now going to multiply my x values by 2 over 1. And so I have the point 8 comma 2, and with 1/4 I would multiply by 4, 16 comma 2. So now if we have a value inside of our function, it affects the x values. And do you remember how moving left and right was the opposite? Like if you saw x plus 3, your gut would want you to go 3 to the right, but it's actually 3 to the left. It was the opposite there. So you sort of have the same kind of opposite thing happening now. You see a 2, which should make you want to multiply by 2, but instead you have to multiply by a half, which is like dividing by 2. The reason we do the multiply by the reciprocal is sometimes you might get a fraction in front, like 3/4, and it'll be easier to multiply by 4/3 than it is to like think of dividing by 3/4. And especially like these ones with the 1/4, I think it's easier to think about multiplying by 4 than it is to think about dividing by 1/4, even though they're the same thing. So that's why we use the language of multiplying by the reciprocal. Now, as we get to more complicated examples, which will happen in this third one, take out my camera again. Again, on my original graph, they have the point 4 comma 2. And what we're going to start doing on our graphs to help us figure out where is there going to be a point? What happens to 4 comma 2 when we have y equals 4 square root of 2x? Well, two things are happening. We have a 4 on the outside. That's going to multiply our y coordinate by 4. And we have a 2 on the inside, which is going to multiply our x coordinate by a half. So for showing our work, one of the things that we're going to do is we're going to start with our original point. I'll do this one in blue because I'm doing the blue graph. And we're going to show an arrow, say that point is going to change. And above the arrow, we're going to write the explanation of what's going to change. So I know, what does this 4 do? It's going to multiply my y value by 4. And this 2 inside is going to multiply my x value by half. If I do that, x by half will be 2, y by 4 will be 8. Can you see that this matches up with the point that they've labeled 2 comma 8? On our green equation, what's going to happen to 4 comma 2? Y value by 2, my x value by a half. 2 comma 4, sure enough, that matches up with that point. And so on, we can do the orange one. Here my y value is going to get multiplied by 2. My x value, because of that half, multiplied by the reciprocal, it's also going to get multiplied by 2. And we would get 8 comma 4. May as well do the last one. In purple, we had 4 comma 2. The half out in front, that would multiply our y value by a half. And the half inside would multiply our x value by 2. So now I can do that. I'm going to get 8 comma 1. Sure enough, that matches up with that point there. So far, we're always doing things either horizontally or vertically. We have to recognize which is which the key is to figure out if something is inside the function or outside of the function. And then everything inside the function kind of is a little bit opposite of what you would think. Left and right was opposite of what you saw, and now you multiply by the reciprocal instead of multiplying by the number. This is very important because if you mix up a couple rules or a couple of the ideas, you're going to get a lot of things wrong as a result. So I would say it's not necessarily hard, but it is easy to get it mixed up. So we do have to pay attention to that. If you look on the next page a little bit, they've got some graphs that we already know, like y equals x cubed. Okay. In the green box, that is how we will always write it. We will always write the y by itself, even though they also wrote it with the 2 on the other side. Can you see that the whole red graph has been squished vertically? And in the orange graph, y equals 2x cubed. The red graph has been stretched away from the x-axis. They've done one particular point. They've taken 2 comma 8. On the green graph, what's changed? The y coordinate's 2 comma 4. On the orange graph, you get 2 comma 16. So as we get to more advanced graphing, we're going to start looking at specific points that we know from our original graph and what happens to them. They also look at adding the reflection right away. Remember that the reflection out in front, so they've got, I'm going to just have it here. A vertical reflection multiplied your y coordinate by -1. The 2 out in front multiplies your y coordinate by 2. We can put both of those together. You can multiply your y coordinate by -1 and 2 at the same time. That's just multiplying your y value by -2. Does that make sense? If you multiplied by -1 and multiplied by 2, you could just do that all at once by multiplying by -2. Watch what happens to our point. We had the point 2, 8. We now have the point 2, -16. Can you see that the red graph has been reflected vertically and also stretched vertically? And they have what happens if you would put that all together. So at the bottom of your page, they have a description about when something is a stretch and when something is a compression. Anytime you're doing multiplying by a number bigger than 1, we're going to say that that's a stretch. Anytime you multiply by a fraction, we're going to say that that's a compression. And when we see some of our examples, you'll get an idea of how we describe that and how we would write that down. All right, we can get ready for example 1.